Let's consider another problem. Evaluate some polynomial for some value of x. Now, the standard school method for evaluating a polynomial can be described in pseudocode as the following. We'll compute the value of each term, ak x to the k, and then we'll add the results. For now, let's assume that each multiplication and addition is one step. Then, computing the value of ak x to the k, this is a product of k factors of x and one factor of the coefficient ak, so it will require k multiplications. We'll need to repeat this for all n terms of the polynomial, and now we have n plus 1 terms, and so adding them will take n more steps. So the first part of the summation is an arithmetic series, so we can sum that up using our arithmetic series formula. And since the number of computations is 1/2 n squared plus 3/2 n, this algorithm is big O of n squared. Now let's consider a divide and conquer approach. Now, if you want to avoid learning anything about how to be creative, look up Horner's method on the internet. But remember, if you do, so can anyone else. If we want to use a divide and conquer approach, the first question is going to be, how do we want to divide the polynomial? One possibility is to split it into two parts. Notice the first polynomial is just a kth degree polynomial. However, the second polynomial can be simplified as, which is the product of some power of x and a polynomial of lower degree. And so here's our divide and conquer. Instead of evaluating one nth degree polynomial, we can evaluate two polynomials of lesser degree. So remember, concrete never hurts. Let's consider a 7th degree polynomial so it has 8 terms and we can divide it up evenly. We'll split this into a cubic part and the remaining terms, where the latter can be rewritten if we factor out an x to the 4th, and we get another cubic polynomial. So now we need to find an efficient way to evaluate a 3rd degree polynomial. So remember, lather, rinse, repeat. We can split a 3rd degree polynomial into a linear factor and x squared times another linear factor. So we need an efficient way to evaluate a 1st degree polynomial. We can split a 1st degree polynomial into a constant and a linear factor, and at this point we're performing basic operations, so it doesn't seem like we can divide this problem any further. Now, note that evaluating this linear polynomial will take 2 steps. We'll multiply a1 by x, and then add a0. This means we can evaluate our cubic polynomial by evaluating a linear polynomial, and then multiplying it by x squared. And so this will take 2 steps, twice for each of the linear factors. 1 step to evaluate x squared, 1 step to multiply x squared by the linear factor, and 1 step to add the 2 terms. So evaluating a cubic polynomial can be done in 7 steps. Note that the school algorithm would require, but this means we can evaluate our 7th degree polynomial by evaluating, which will take 7 steps twice for each of the 2 cubic polynomials, 3 steps to evaluate x to the 4th, 1 step to evaluate the product of x to the 4th and the cubic, and 1 step to sum the 2 terms, for a total of 19 steps. And the school algorithm would take. What if we had a 15th degree polynomial? The school algorithm would require, the divide and conquer method would take 19 steps twice to evaluate 2 7th degree polynomials, 7 steps to evaluate x to the 8th, 1 step to multiply x to the 8th by one of the 7th degree polynomials, 1 step to add, for a total of 47 steps. If we take a closer look at our algorithm, we see that there is a step that requires a larger number of steps than the other, which is to say, evaluating that factor of x squared, x to the fourth, or x to the eighth. We had to do this because of how we divided the polynomial. Could we divide it differently? Since the problem is evaluating x to the power n, what if we simply divided our polynomial so we had to multiply by x? For a cubic polynomial, we could have it rewritten as, so we need some number of steps to evaluate a second degree polynomial, 1 multiplication by x, 1 addition by a0, and again, lather, rinse, repeat. We could rewrite our quadratic polynomial as, so we need some number of steps to evaluate a first degree polynomial, 1 more multiplication, and 1 more addition. This insight leads us to something called Horner's method. To evaluate a polynomial, for convenience we'll reverse the order of the terms, we'll split off the constant, and note that all the remaining terms have a factor of x. So we'll remove a factor of x from the remaining terms, then lather, rinse, repeat. And so we can evaluate our polynomial as a0 plus x times a1 plus x times a2 plus and so on. For example, let's suppose we want to evaluate a cubic polynomial. So splitting off the constant and factoring x from the remainder gives us, and so we can evaluate f of x by finding, and so evaluating f of 5 will require 1, 2, 3 additions and 1, 2 multiplications for a total of 5 operations. In contrast, the school algorithm will require 3 additions but 5 multiplications for a total of 8 operations. To determine the time complexity of Horner's algorithm, let's consider a few cases. For a polynomial of degree n equals 1, we need 1 multiplication, x by the coefficient, and 1 addition for a total of 2 operations. For a polynomial of degree n equals 2, we'd evaluate this as, where the linear term requires 2 operations, and we need 1 more multiplication and 1 more addition for a total of 4 operations. For a polynomial of degree n equals 3, we'd evaluate this as, where the quadratic term requires 4 operations, and then we need 1 more multiplication and 1 more addition for a total of 6 operations. So it appears that for a degree n polynomial, we need 2n operations, so Horner's method is big O of n. The school method is big O of n squared, so Horner's method runs significantly faster, although in practice we're unlikely to need a high degree polynomial, so the increase in speed doesn't seem worthwhile. If a machine can perform 1 billion calculations per second, then a 1,000th degree polynomial would require about 1/500th of a second, while Horner's method would require 1/500,000th of a second. While the difference in time seems almost imperceptible, note that we don't often require evaluating high-degree polynomials, but we often evaluate millions of polynomials, so the time savings of Horner's method becomes useful. To evaluate 1 million polynomials of degree 1000 would require about half an hour using the school method, but only 1/500th of a second using Horner's.